Hello and welcome everyone. In this lecture, I'll be discussing about the critical speed of shaft carrying single rotor without damping and with damping. So, when a rotor is mounted on shaft, its CG is usually does not coincide with the axis of rotation. So, we can I can explain over here. This is our rotor which is mounted on the shafts. So the usually the CG should be over here, but it is slightly displaced. So what will happen? This will cause the unbalance. This displacement of CG can be due to the eccentricity, can be due to lack of straightness of the shaft, can be due to the bending of shaft under action. Then there is non-homogeneous rotor material is not homogeneous, unbalanced magnetic pull in case of electric machinery. As a result of this, initial eccentricity of the center of gravity from the axis of rotation, shaft is subjected to centrifugal force. There will be the centrifugal force, and this centrifugal force acts radially outward, which makes the shaft to bend in direction of eccentricity, and this further increases the eccentricity and hence the magnitude of centrifugal force, because of which the in this way the effect is cumulative and the shaft can fail. So this unbalanced centrifugal force which is acting a shaft starts to vibrate in the direction perpendicular to the rotation of the shaft, which is called as whirling of shaft. And the speed at which the shaft starts to vibrate violently in the direction perpendicular to axis of shaft rotation, it is called as critical speed of shaft or whirling speed. Now let us discuss about the here. Let me repeat: the speed at which the shaft starts to vibrate violently in direction perpendicular to axis of shaft is known as critical or whirling speed of shaft. So here what will happen, let us explain with this figure. Consider a vertical shaft having negligible inertia and carrying a single rotor. There is a single rotor. Now the shaft is stationary condition while the shaft over here is in rotating condition. This is our stationary shaft. O is the point of intersection of the bearing center. This is the bearing center line with the rotor. There is a point of intersection over here. S is the geometric S is geometric center of rotor, while the G is the CG of rotor, center of gravity. M is the mass of rotor. E is the eccentricity, which means the distance between the CG and the center of geometric center of rotor. Now here we can see in the rotating condition there is a deflection of the shaft, which is Y from the center O. This is the bearing line and rotor axis center over here, bearing line and rotor center. So there is a deflection. K is the when there is a deflection there will be some stiffness of shaft. So the transverse stiffness is suppose K Newton per meter. Omega is the angular speed of shaft, and omega n is the natural circular frequency of lateral or transverse vibration of shaft. Now we have to, when a shaft is rotating condition, there are two forces. First one is centrifugal. Over here we can see there are two forces. This is the centrifugal force, and this is our restoring force. Restoring force. So this is centrifugal force, which means force m omega square r. We know that centrifugal force, so here the r will be equal to y plus e. Same way here the restoring force, we know that the spring force is k into x, the stiffness k of the shaft, and here this will be the distance y, so it will be equal to k into y, which will act in radially. This force will act in radially inward direction, while this force will act in radially outward direction. So for equilibrium of there will be the centrifugal force will be equal to the restoring force. So what will happen, we will see over here. So there are two forces, centrifugal and restoring force, and both forces are equal. So by solving this equation, this will come into the multiplication of this, and if we put this over here and y we take common, so we will get the equation of the y as this. Now we will divide by k above and below, we will get this, and if we take m below, so we will get this. So we know that the k by m is equal to omega n square. So we will get the final equation of y as omega by omega n square e upon 1 minus omega by omega n square. So this is the equation of the deflection of shaft. Now from that equation we can see that the angular speed of shaft omega increases, the deflection of shaft increases, and when the omega becomes equal to omega n, the deflection will become infinity. So here we can see that the y deflection is proportional to the omega. So as the omega increases, the deflection will increases, but when the omega becomes omega n, so this will be the critical omega, this will become omega c. When omega is equal to omega n, omega becomes omega c, which means the critical or whirling speed. So for critical or whirling speed, we can get the critical and whirling speed as equal to under root k by m or under root g by delta. And this is the angular speed. Now for linear speed, we will get critical speed nc is equal to omega upon 2 pi. So this will be the critical speed in rps. Now this equation can be rewritten in terms of omega c for critical speed in the deflection, instead of omega n there will be omega c. Now from this there are some range of speed which we know that the from the critical speed equation, if the what will happen if the shaft speed is less than critical speed, greater than critical speed, and very very greater than critical speed. So first let us discuss the omega. When shaft speed is less than the critical speed, what will happen? The deflection y and eccentricity e are in opposite direction. Here the e and y are in opposite direction. The rotor rotates with heavy side outwards, and in this speed range the deflection y increases with the deflection y increases with the increase in omega. When the shaft speed is equal to the critical speed, for that condition the deflection y tends to become infinitive. This y tends to become infinitive, and this may lead to failure of shaft. When the speed of shaft is greater than the critical speed, we can see from here the deflection is negative. Deflection is negative. So and eccentricity is also on the same side of the geometry center. So the rotor rotates with light side outwards, and in this speed range, as the omega increases, the deflection approaches to minus e. When the omega is very very greater than the omega c, which means this case, there will be so g approaches to the axis of rotation, which means the y is equal to e. This principle is used in running high speed turbines by speeding up the rotor rapidly beyond the critical speed. When the y approach is equal to minus of e, which means the deflection and eccentricity both are compensated over here. So this was about the critical speed of shaft carrying single rotor without damping. Now next we will discuss about the critical speed of shaft carrying single rotor with damping. Now for with damping case, the all parameters will be same, but due to existence of damping there will be the damping force, and the damping force will be equal to the c omega y, which means the c is the damping coefficient, omega is our angular velocity, and y is our deflection. The centrifugal force, suppose the cg is over here, the centrifugal force acting will be in this direction, which will be the m omega square a, because over here from center the distance is a. So and the restoring force will be acting in this direction, which will be equal to k into y, and the damping force, suppose the rotation is in this direction, the damping force will be in the opposite direction, which will be the CM y, sorry, C omega y. Now we have to resolve the due to damping force, the point O, S and G no longer on the same axis because of damping force. They will not be in the same axis, and this is the cross section we can see over here. This is our centrifugal force, and this will be our Cm omega y. This is our damping force, and this is the Kx, which is the restoring force, or which is called as the spring or stiffness force, Ky. So here we can see this will make psi angle, and this will make a phi angle, G and S. Here there will be the C omega y, and this will be the M omega square A, and Kx will be Ky in this direction, K into Y. So there are two components of this. First one is cos component and another one is sine component. Same way over here we will get the eccentricity E, eccentricity, which means the center of rotor, and CG, both are in displaced condition. S and G, the distance between both center of rotor. This is our rotor center, and this is our CG. This is called as eccentricity. So the cos and sine component will be this. Same way for A, there will be the A cos psi and A sin psi. Now we have to resolve all the horizontal forces which are acting and vertical forces. So as you can see, the horizontal forces is M omega square A cos phi and Ky, and vertical force is M omega square A sin psi and C omega y. So what will happen by resolving the horizontal force? Because we will get the sigma fx and sigma fy. Now as we can see, the cos m omega square A acts in positive direction while Ky acts in negative direction, so this will be taken as minus. Same way for vertical forces, this will be in the upward direction, and C omega y, which is our damping force, which acts in opposite direction, so this will be considered as negative, this will be considered as negative. So that we can see in this equation number A and B, we can see. Now from this figure, A sin phi will be equal to E sin phi, and A cos psi will be equal to Y plus E cos psi. These two we can see in this equations. So we put the value in the above equations, these two equations. We put the value of A sin psi in this equation and A cos psi in this equation. We will get the value of E cos psi and E psi we will get by resolving this equation in terms of y, e and phi, which are non-terms. So we can make the y as, we can find the deflection from this equation, and on substituting value in the second equation we will get the c omega y equal to m omega square. Sorry, here first we put the value of a cos phi in the this equation, and in the second equation we will put the value of a sin phi, and we will get this equation number f and e. So taking the ratio of both equation we will get the sin of phi upon cos phi, which is equal to the tan phi. So this will be tan phi, and as we know that the c omega by k minus m omega square, which means if we divide by k we will get this 2 zeta omega by omega n upon 1 minus omega upon omega n square. So we can find the angle phi. Now we can write here omega n is equal to omega c for critical speed, and this is the equation gives the phase angle between the eccentricity line and deflection line here, and the angle by which the deflection lags. This the phi. Now we will discuss about the variations. Here we can see from there is a phi, and this is the horizontal and vertical side, and this is the hypotenuse. So we will get the sine is equal to opposite upon hypotenuse. Same way we can find the cos, which is equal to adjacent upon hypotenuse. Same way, and we can find the deflection y. Now from this equation, here it is given that the deflection of geometric center of rotor from initial undeflected position for whirling of shaft are same as that of the force damped vibration with rotating and reciprocating unbalance in case of force damped vibration due to rotating or reciprocating unbalance. The unbalance was in terms of small mo, whereas in this case the unbalance is defined in terms of total mass m with eccentricity e. So we will discuss the various possible phase angle. Here the first phase angle is when the angular speed is lower than the omega n and phi is equal to 0, which is heavy side out. So this will be the first case when omega is less than omega n. Same way here it is given for the omega less than omega n, which means the angle phi is between 0 to 90 for heavy sideways. Same way for omega by omega n is equal to way which is considered over here, and phi angle is 90 degree for omega greater than omega n, and which is between 90 and 180, and last one is omega is very greater than omega n, y is equal to minus e, and phi is equal to 180 degree for light side out rotors, about its CG. So these are the various possible phase angles we can see. So this is it for today's lecture. Thank you very much for watching.